In this video, I'm presenting a use case of a problem I initially planned to solve by finding a developer to build the system. At the same time, AI and vibe coding platforms began making complex development workflows more accessible, and I realized I could try diving in myself and see how far I could get. Here, I show how I reached a working solution despite having no prior development experience, so let's dive in and take a look. What you're seeing here is a highly detailed illustrated city map, closely matching the structure of the real city. Every street and every building is represented, all rendered at a very large scale. The map itself reaches dimensions of roughly 40,000 pixels in width and around 20,000 pixels in height, an unusually large format for image generation workflows. Here on the second screen, you can see the original working method. I used Dream Studio to restyle an existing image, uploading a source file, selecting a style, adjusting parameters, and generating the result. This is how the map was built, layer by layer, starting from a fully realistic base and gradually moving toward the illustrated style. The challenge emerged with scale. These tools work optimally on images around 1024 by 1024 pixels, while the full map consists of hundreds of such sections. Initially, we tried manual workflows, slicing, Photoshop imports, stitching techniques, but the results lacked consistency. Styles varied between sections, and visual coherence was lost. At that point, manual work was no longer a viable option, especially when maintaining stylistic consistency at this scale. The problem became a technical one: how to standardize and automate the entire process. This is where the focus shifted toward automation, and eventually toward building a structured pipeline that could control the process systematically and reliably. Let's move on to the next screen. At first, I considered building the solution directly in Comfy UI. I explored creating a pipeline to handle the entire process, but it quickly became clear that this approach wasn't user-friendly, especially for a client and without a proper UI. At that point, ChatGPT became the orchestrator of the entire system. Every technical, architectural, and process-related decision went through ChatGPT. While each platform has its own AI capabilities, the overall reasoning and integration were managed through ChatGPT. From there, I started designing the UI in Figma. Based on that work, I moved to local development in Visual Studio, and then deployed everything to Replit, including the back-end APIs and integrations. Later on, I experimented with Lovable to further refine the UI. In hindsight, this step wasn't strictly necessary, but it helped clarify direction. Eventually, everything was consolidated back into Replit and connected to Supabase. The path could probably have been shorter, and I might not have needed every vibe coding platform along the way. But without prior experience, I had to go through the full journey to understand what I needed. And in the end, it resulted in a working, user-friendly product. This slide shows how I validated the AI core before committing to a full production system. I initially tested Comfy UI, running on a rented RunPod GPU instance. While technically powerful, this approach required manual node graph configuration and wasn't suitable for end users or a scalable product, so it was rejected at this stage. To properly validate the model behavior, I moved to a code-level pilot using GitHub, Google Colab, and the Stability AI Image API. This allowed me to directly test style transfer parameters and output consistency in isolation. Once the model and API behavior were fully validated, I was ready to transition toward a production architecture, which we'll look at in the next slide. What you're seeing here is the core architectural idea behind the system. This product is built to restyle extremely large images, sometimes up to 40,000 pixels wide, without flattening or destroying the original. Instead of treating the image as one heavy file, we separate the challenge into three different technical layers. First, AI processing. The image is conceptually divided into 1024 by 1024 tiles. That's not for upload. That's specifically for the Stability AI model. Only individual tiles are sent to the API. The full image is never processed at once. Second, file transfer and storage. Uploading a massive image directly would create network bottlenecks. So instead of splitting by resolution, we split by file weight, using chunked uploads to ensure reliable and scalable transfer to storage. Third, browser preview. Before anything is uploaded, the browser creates a temporary blob URL and renders the image instantly. The grid you see isn't baked into the file. It's calculated dynamically in the UI. So visually it feels heavy, but architecturally it's lightweight. The important idea here is separation of concerns. Tiles for AI, chunks for upload, LOD for preview. Each solves a different bottleneck, and together they make very large images interactive. The implementation details of the pipeline are shown in the next slide. This slide focuses strictly on the preview layer and upload architecture. On the front end, the system is built with React 18, TypeScript, and the Canvas API. Large images are never uploaded just to be previewed. When a user selects a file, the browser generates a blob URL and renders it locally. No server round trip, no temporary upload. Rendering is viewport-based. Using Canvas, transforms, and CSS matrix calculations, only visible regions are drawn, similar to a lightweight LOD renderer. The grid overlay is computed dynamically in React. It's not baked into the image. Tile coordinates are calculated in the UI layer using deterministic math. Now, upload is treated as a separate pipeline. Because of replit reverse proxy timeout in approximately 60 seconds, Superbase 50 MB file guard, browser memory limits. We implemented size-based chunking, not tile-based chunking. The file is split into approximately 4 to 5 megabyte chunks. Each chunk is uploaded via post/upload-chunk/:ID. Retries use exponential backoff. Chunks are reassembled server-side before final validation. Before upload begins, large PNG are optionally converted client-side to JPEG to reduce transfer size. So, architecturally, preview to browser only, upload to chunked streaming assembly, to back-end persistence, to Superbase storage. This separation solved proxy limits, memory pressure, and blocking uploads. Now we move to the processing and persistence layer. Once the original image exists in Superbase storage, the system never edits it directly. Tile extraction is done using Sharp, Node.js. We cut 1024 by 1024 tiles on demand. Not up front. This avoids generating unnecessary derivatives. Each tile is normalized to valid model dimensions before being sent to Stability AI API. Processing is parallelized. Tiles are dispatched asynchronously, no sequential bottlenecks. After AI processing, outputs are written back to Superbase under Outputs. Metadata is recorded in PostgreSQL. The database stores session ID, original path, tile IDs, processing status. The database is orchestration, not storage. Tile state transitions are explicit, pending to processing to complete, to session, ready. We also implemented dimension validation and scaling guards before model calls to prevent SDXL constraint failures. Finally, recomposition is done non-destructively in the browser. The original image remains untouched. AI outputs are layered precisely using Canvas coordinate alignment. Export is a final composite, never destructive. So technically this slide is about Sharp-based tile extraction, stability, AI integration, Superbase storage, structure, PostgreSQL session, tracking, parallel processing orchestration, deterministic recomposition. This is the production-grade backbone behind the visual system. This is the entry screen of the system. Here we have user access and application routing, including authentication and password handling. For this demo, we'll go straight into the main application. This is the main workspace. The primary action is uploading an image using the upload button. Once the image is loaded, a grid of tiles is generated automatically over the canvas. On the right side, there's a control bar for zooming, panning, scaling, and fitting the image to the canvas. All of these interactions also work naturally with the mouse and scroll wheel, similar to Google Maps. The preview system uses LOD, level of detail, rendering. This allows smooth navigation from low-resolution previews up to full one-to-one resolution without pixelation, depending on the zoom level. Let's move on to the selection menus. This drop-down controls which tiles will be sent for restyling. The first option selects all tiles at once, and you can see an indicator showing how many tiles are currently selected. Any selection can be cleared from here. There's also an inverse selection option, and the ability to hide the blue selection overlay if it interferes with visual inspection. Even when the overlay is hidden, selected tiles remain active. Each tile has a unique logical index based on its row and column position. You can also save selection groups and name them, useful when working on the same image over multiple sessions and returning to specific areas later. On the left and top edges, there are row and column selectors for fast bulk selection. Tiles can also be selected or deselected manually. For this demo, I'll select a limited number of tiles. In the current version, API execution is sequential, so processing a large batch would take time. This is a known bottleneck by design. The next phase introduces controlled parallel execution, API load balancing, and horizontally scalable processing to remove this constraint. A serverless distributed worker model is the long-term target architecture. Now let's open the Restyle panel. This interface closely mirrors the Restyle controls from Stability AI's Dream Studio. Here you can enter a prompt and negative prompt, upload a style reference image, and control parameters such as composition fidelity, transformation strength, restyle intensity, number of outputs, and seed control. You can also save these parameter presets and reuse them later. Once the settings are ready and the desired tiles are selected, we trigger the restyle process. At the top, you'll see a step-by-step progress indicator covering the full pipeline: upload, processing, and completion. This feedback layer was extremely helpful during development, especially for debugging load and performance issues. There's also a status indicator confirming when the original image upload has completed. In this case, it happened very quickly, so it's barely noticeable. Once processing finishes, we can zoom in and inspect the new style applied only to the selected tiles. On the Layers panel, which is intentionally similar to Photoshop, a new layer is created above the original image. Only the processed tiles are visible. All other areas remain transparent. From here, we can export the result. By default, exporting downloads a composite image combining both layers. However, just like in Photoshop, the base layer can be disabled. This allows exporting a transparent PNG containing only the rendered tiles, aligned perfectly to the original resolution. This is especially useful for continuing work in Photoshop without dealing with manual alignment or positioning. At the moment, Photoshop is still part of the workflow for inpainting, mainly to smooth seams between tiles. Full continuity between tiles is not yet fully solved inside the system. That said, I'm currently working on an automatic inpainting feature, using a different model specifically to address tile seam blending. Additional features are also in development, including video outpainting. That's the walkthrough. This is my first full vibe coding project, and it's been both exciting and challenging. Coming from a background in motion design, editing, and animation, it's very clear how fast new tools and models are reshaping the field. On one hand, established workflows are being replaced. On the other, there's a real sense of creative possibility becoming more accessible than ever. If you have feedback, insights, or ideas, I'd love to hear them. I'm also open to collaborations, and if you're interested in this system specifically, feel free to reach out. And thank you to everyone who made it all the way to the end of the video. And just to clear one last thing up, no, I don't suddenly have a heavy British accent. This voiceover, like parts of the system you just saw, is AI generated, seemed appropriate.